And we're ready to go.
Welcome to another live session. Lots happening in the world of astronomy, so the floor is open for your questions.
All right, the first question is, have any other theories developed which are good enough to challenge the Big Bang model?
Short answer, no. The Big Bang model of a early hot dense phase of the universe, representing its birth 13.8 billion years ago, is essentially unrivaled. Early in the history of this subject, in the mid-20th century, the rival theory was the steady state theory, which actually accommodated the expansion of the universe and had matter appearing at the rate of about 1 atom per cubic meter per century in the vacuum of pure space, keeping the universe sort of unchanging over time. So it was a non-evolving universe in that way, even though there was expansion. And the steady-state theory had some traction through the 50s into the 60s until the discovery of the microwave background. That cosmic radiation signature seen all over the sky at a temperature of 3 Kelvin is in perfect accord with the idea of a hot early dense phase where the temperature of the radiation dilutes and cools with the expansion to a temperature of 3 degrees above absolute zero now. So that really cinched the Big Bang as a viable theory of the universe, because it's very hard to explain that radiation anyway other than the Big Bang. And in fact, that's the bar that any alternative theory has to pass. It has to be able to explain all the evidence we have, especially the microwave background radiation, with an alternative type of idea. And so far, that's not been possible. There are not, and in fact, theorists have not quite given up trying, but they are so convinced that the Big Bang is a viable explanation for the universe, the early universe, that I think there are hardly any theorists working on alternative theories.
All right, the next question comes from Bob. Do we know where the actual center of the universe is?
So cosmology is based on the fact that of the Copernican principle, the idea that our location in space, if not in time, is not special. And nothing we have seen in our observations with telescopes has violated the Copernican principle. Our solar system is not a special location in the Milky Way. Our Milky Way is not a special galaxy among the thousands of spiral galaxies we've seen. And even our large chunk of the universe, maybe a few 100 million light years across, containing hundreds or thousands of galaxies, does not seem to be strange or special compared to any other part of the universe. So there's nothing special about our location. The fact that galaxies are all moving away from us also does not implicate us as being at the center, because it's a cosmic expansion in 3 dimensions, everything moving away from everything else. So if we were located on another galaxy, near or far, we would see exactly the same expansion. So no observation yet made, I can make this a categorical statement, shows any special location for us in the universe. And definitively, we are not at the center.
All right, Stan has a question that is, there have been theories in the past about some possible planet, like Planet X, well beyond the orbits of Neptune and Pluto. Has that been disproven, or could New Horizons' journey lead to its discovery if its path were perturbed as it journeys through the Kuiper belt?
So it's a good question. What's out there beyond the orbits of Uranus and Neptune? And New Horizons is going to give us one view of that. So there's sort of 2 parts to the question. Are there substantial sized planets beyond the orbit of Uranus and Neptune? And second, what will New Horizons bring to the table as it passes Pluto and heads out into the Kuiper belt? As far as the likelihood of there being Pluto-sized or larger dwarf planets beyond in the Kuiper belt, the odds are very high that there are such planets. Eris was discovered a few years ago, and Eris is statistically it's the same size as Pluto. The actual number given for it is a few percent bigger. So Eris is bigger than Pluto, and there are another handful of objects that are close to Pluto in size that have been found in the last 5 years. The best guess is that when surveys are completed for objects of about that size, there'll be another half dozen or so. So we will, in the end, have found 10 to 12 Pluto or near Pluto-sized objects in the Kuiper belt, and very many that are 2 times smaller, 3 times smaller, 10 times smaller. So there's a lot of fairly large objects out there, bigger than most moons, and in the size range of small dwarf planets. They're spread over a very large volume of space because they're not only covering a very large number of square astronomical units, if you like, out beyond the orbit of Neptune. The Kuiper belt extends from 40 to 80 astronomical units, so it's huge. But they also extend above and below the plane of the ecliptic, which is the orbital plane of the Sun and most of the giant planets. So it's very hard to search that thoroughly for small objects that are far away. And most of it's done with telescope networks of about 1 to 2 meters in size. And that work's underway, and that's where the estimate of eventually a dozen dwarf planets comes from. New Horizons, of course, took a particular path towards the Kuiper belt, the trajectory that allowed it to pass with some assistance from Jupiter early on in its trajectory, which actually saved it 4 years getting to Pluto, is now whizzing out through the outer solar system along a particular path into the Kuiper belt. The odds that New Horizons itself will encounter another Pluto-sized object are very small. New Horizons is going to keep sending back data, but its cameras are not big enough to do big surveys, and it's not really equipped for that kind of a detection experiment. That's what it wasn't designed for that. So basically, the odds are very small that New Horizons itself will discover one of these dwarf planets. But on its way through the Kuiper belt, New Horizons will sample what's in the Kuiper belt. We'll do a sort of representative survey, if you like, of how many big, medium, and small-sized rocks there are, down to asteroid size and up to dwarf planet size. So it's going to give us an extraordinary, great deal of information about the Kuiper belt, and especially a census of what's out there, if not an inventory of the biggest objects.
Right, there are several questions about Pluto, and so we'll start with one from Howard. Considering how different Pluto is with its apparently young surface, such a small body having an atmosphere, along with its very eccentric orbit, is it possible Pluto was not formed in our solar system 4.5 billion years ago?
Right. So Pluto is obviously the exciting destination and a wonderful validation of the team that worked so hard against really incredible odds to get that mission off the ground and launched and sent for a decade out into the solar system. As I'm sure you all know by now, that mission, or the Pluto concept, was canceled several times by NASA. It was resuscitated. Extraordinary persistence to get that mission out there, and it's been rewarded. And of course, after it was launched, the astronomers went and demoted Pluto to a dwarf planet status, and I think some people just outside the astronomy community just sort of forgot about it and thought, oh, it's not very interesting anymore. It's been very surprising, of course, what it's found. To take that particular question, yes, it is entirely possible that Pluto is a captured object, and in fact, the idea that Pluto did not form along with the other planets in the outer solar system is definitely an oddball. It has a highly elliptical orbit, it has a highly inclined orbit, it's much smaller than the other 4 gas giant planets. And the best guess, although it's very hard to prove, is that it is indeed a captured orbit object. And if it is captured, of course, then we don't know exactly when it did form. So we haven't got an age for Pluto that says that it's exactly the same as the 4.6 billion years of all the other planets in the solar system.
All right, you kind of covered the question that Stan had about why Pluto's orbit is tilted relative to the planets in the solar system. But if you have anything else to say, that's his question. And then he also wants to know if you have any new books planned. He's running out of reading material.
Oh, there's lots of good reading material out there. So back to the orbital tilt, or the nature of Pluto's orbit. Its orbital parameters are suggestive of the fact that it was captured. But of course, planets interact with each other and they can perturb each other in their orbits. So people have worried that it's also possible that Pluto could have been within the solar system in a more regularized orbit, and interactions with Neptune in particular sort of scattered it into a highly elliptical and inclined orbit. And those models, so people have not, they've considered that possibility. It's actually very hard to arrange that. It is much more likely that it was captured. As far as books, well, I just published a book on the future of the space program, taking a deep breath for the next one. And at the moment, the two ideas I'm mulling, which I'll start writing later this year, are a book on great mysteries of astronomy, which will probably be more cosmology, supermassive black holes, dark matter, dark energy, and so on, and the very current information on the state of our understanding of those and our search for better understanding. That's one idea. And the other one I'm exploring is a sort of retake on a book that Primo Levi wrote in the 1950s about the periodic table, where he, without anthropomorphizing the elements too much, he sort of turned the story of, in his case, 20 chemical elements into allegories, human allegories. In his case, it was the history of the Second World War and his time in the concentration camps in Germany, where he was telling, human stories overlaid on the chemical story of these elements. My idea would be to tell the astronomical story of the elements, since they were produced inside stars, and overlay that with more of a human story of how they were found. So I'm not sure how that's going to go. I'm not sure which of those books will get written first.
Okay, the next question is from Gerald. My understanding is that astronomers have found that the total amount of mass energy in the visible universe is 10 to the 53rd kilos. The total amount of gravitational mass energy is a total of 10 to the minus 53rd. So the universe came from nothing. Well,
that's certainly one way of framing it, because the universe, if you ask what is the, how can we characterize the entire universe, clearly the universe has a large amount of mass and energy in it. It has radiation, more photons than particles, 10 to the 80 particles, plus the dark matter particles, plus about 10 to the 88 photons. So there's some mass energy content of the universe, but the universe also has the energy of its expansion. So it has gravitational potential energy created by the expansion of that amount of matter into a very large volume of 92 billion light years across, or 46 billion light years in any direction to the visible horizon. In the sense that it could be created from nothing, that alludes to an idea in cosmology that in the inflationary era, the seeds for galaxies were actually quantum fluctuations that were expanded by inflation by 35 or 40 orders of magnitude to the size of galaxy patches, where small perturbations in the initial mass distribution eventually grew and grew until the galaxy collapsed into a set of stars. And viewed in those terms, from quantum creation, it is indeed possible that the impulse for the Big Bang expansion was the result of a quantum fluctuation of an early, dense initial state. So Alan Guth, the architect of the inflationary theory, has famously said the universe was a free lunch in those terms, because you can borrow energy from the vacuum. That's well understood physics. And if you borrow the energy for a very short time, the amount of energy can be prodigious. And in fact, if you take it to the Planck time, 10 to the minus 43 seconds, our earliest possible understanding of space and time, then the energy you can borrow is enough to inflate a universe that will eventually contain 100 billion galaxies and all the photons per particle that I described earlier. So yes, you couldn't get the whole thing for nothing.
All right, Gerald also asks, if the universe is expanding by falling outward through inflation, what is it falling into?
It's expanding, but it doesn't have to be expanding into anything. Our edge of the universe determination is based on the limit of time rather than the limit of space. So as we look out with especially the Hubble Space Telescope, the deepest images we can make are with the Hubble, and eventually will be with the James Webb. The limit we see is a limit in time. We've looked back now to 95, 97% of the age of the universe, 97% of that 13.8 billion years, so back to about 100 million years after the Big Bang, maybe 200 million. And that's the time when the first galaxies formed. So looking further out than that essentially leaves us with darkness, and it's called the Dark Ages. It's a time we understand and anticipate should be present in the history of the universe, the time between the fading of the glow of the Big Bang, when the entire universe was essentially glowing, with visible light, maybe a few 100,000 years after the Big Bang, fading to microwaves and radio waves in the present day. So the limit we see is the limit of time. We just run out of photons because collapsed objects like stars and galaxies no longer exist looking that far back. But there's no sense that the edge of space has been seen with these telescopes. And since space is measured to be flat by the COBE and then WMAP satellites, microwave radiation experiments tell us that space is flat. It's Euclidean in 3 dimensions. There's no reason to postulate a curved entity or some self-contained closed universe. Space is flat, and it could indeed be infinite. There's no observation to refute that premise.
Okay, the next question is, in the news today is a planet being described as Earth's twin found by Kepler. I thought Kepler was out of service. What's it doing now? How is it still finding planets?
Kepler is in what's called its K2 phase. So yes, Kepler lost some substantial pointing capability, which compromised its primary mission. And I would say it's doing better than limping along. It's taking data, and in its so-called K2 mission, its secondary mission with reduced capability, where it's now looking at a larger area of sky. There's no longer any point in it just staring at that one patch of sky, trying to measure fainter and fainter planets, because it doesn't have the precision of pointing to be able to pick them out in a very crowded field of stars. So Kepler's now broadened its view and is still capable of finding planets, not with the efficiency that it had for its first 4 years. I think it's found 25 or so confirmed exoplanets in its second phase, when it was supposed to be dead. So it's finding them at a lower rate, but the planets it's finding are still interesting. And this discovery, announced just today, maybe the press conference was yesterday, is another Earth clone, and we're finding increasing numbers of Earth-like planets. I think the body count now from Kepler, where most of this increase in the last year has come from just shoveling the data that it took in its first 4 years rather than new data that it's found in its K2 mission. It's up to about 800 planets within a factor of 2 or 3 of the size of the Earth, which is an extraordinary number. That's 800 roughly Earth-like planets. Perhaps 1 in 10 of those, so nearly 100, are inhabitable in their habitable zones. And this one that was discovered today is getting as close to an Earth clone in terms of mass of the planet, distance of its orbit, period of its orbit, temperature on its surface, likelihood that it's rocky and Earth-like, as any planet that we found so far. So very exciting to be sort of homing in on Earth clones, but that shouldn't obscure the fact that statistically, if we don't obsess about finding something that's exactly like the Earth, it's already found hundreds of Earth-like planets.
Okay, the next question is from Michael. Are there chemical or non-biological reactions that could create methane? Basically, where does methane in planetary atmospheres come from?
Methane is, so it's a good question. I mean, methane is a very simple molecule involving nitrogen and hydrogen, two of the most abundant ingredients in the universe. And methane is produced quite easily in the near vacuum of space, in interstellar space, in places where stars are forming. So in the molecular clouds, the sort of cold, fairly dense regions, where dense in this case means 1 atom per cubic centimeter. It's not that dense at all, really, compared to the air we're breathing. In these cool regions where stars eventually are going to form, it's quite easy for molecules to form. They form by photochemical reactions. I mean, basically, there's enough free energy from ultraviolet radiation or cosmic rays to create reactions that produce methane as a byproduct. And also other molecules. There are molecules with up to 22, maybe I think the record is 30 atoms in interstellar space. Methane, therefore, is one of the simpler molecules you'll find in interstellar space. And so those molecules are abundant in the regions where stars form, and then when planetary systems form, the methane is naturally incorporated into those planetary systems. And since hydrogen is the most abundant atom in the universe, and nitrogen is after helium, the next most abundant atom, methane has quite a significant concentration cosmically. So there's significant amounts of methane in the outer solar system.
Okay, the next question is about the Pluto and Charon system. I've seen it in the news that Charon does not really orbit around Pluto, that they orbit around each other. Can you talk a little bit about how this works?
Yeah, it's the idea of a common center of gravity. So we tend to think of the planets orbiting the sun, and the sun is sort of fixed at the center of the solar system. The planets go around it, but that's not true. Newton's law of gravity is equal. So the force exerted on object A by object B is the same as the force exerted by object B on object A, and so they both respond to the force. What that means in the solar system is that Jupiter being by far the most massive planet, the sun is in fact being pulled by Jupiter, just as the sun holds Jupiter in an orbit. And so they both orbit a point that's around the edge of where the sun is. So while Jupiter does indeed do its big orbit with a distance of 5 astronomical units, the sun does a little pirouette, sort of spinning about its edge every 12 years. So that's the principle, and you can see, or the physics is fairly simple, it's just like a lever arm, that the more massive the planet and the closer the planet is to the star, the more it will pull the center of their combined orbit away from the center of the more massive object. And the logical endpoint of this, of course, is when you have, say, a binary star system, where you have two equal mass stars, and they will just orbit a point midway between them. So any intermediate situation is just easy to imagine. You just can literally visualize a balance beam or a seesaw, child's teeter-totter, where the one star is on one side, the other star is on the other side, or the star is on one side and the planet is on the other side, and you just figure out what the balance point between them should be. And that balance point is going to be the center of their co-orbital motion. And so that's what we have going on with Pluto and Charon. It's just based on the mass ratio between the planet, the dwarf planet in this case, and its moon. Now, of course, we know that Pluto has a small raft of tiny little moonlets. We'll even just call them moonlets because they're really small, almost asteroid-sized. And they also affect its orbital motion. But Charon is by far the biggest moon, so most of the orbit of Pluto and Charon is determined by those two objects.
All right, the next question is, how will the solar system travel through the Milky Way galaxy in the future? And will the appearance of the Andromeda galaxy, once it collides with us, change how that works?
Right, so the question is alluding to an important feature of our situation in the Milky Way galaxy. So we know that the sun and the solar system and the stars nearby us in the sky and in space are traveling around the center of our galaxy. We're about 2/3 the way out in the disk. And it's been known for decades that the orbital time at the sun's location is about 240, 235 million years. So the solar system, the sun and the planets, have been around the Milky Way since the Milky Way formed. The Milky Way we formed at least 10 or maybe 11 billion years ago. So you can do the math, and that's 45 or so orbits of the Milky Way we've done completely since the Earth formed. Well, actually, since the Milky Way formed, but since the Earth formed last, it's 4.5 divided by 1/4. So that's about 18 times round. So that's the orbital time, but in fact, the galaxy has a finite thickness. The disk of the Milky Way has a finite thickness, and the solar system and other stars around us have what's called a Z motion, Z being that third dimension, up and down, in and out of the disk, X and Y being in the plane of the disk. And so our Z motion, which has also been known for decades, is not zero. In other words, we're not perfectly orbiting in the plane of the disk. We're slanting in and out of the disk. And that undulating motion is a sinusoid. It's just a periodic component of our motion along with the periodic motion around the Milky Way. And the period of that sinusoid in and out and then in and out again of the Milky Way disk is about 26 million years. So that's what we're doing. At the moment, we're somewhat above, depending on how you want to look at it, above the Milky Way plane, heading towards it. So in the future, where that means millions of years, we, meaning the sun and the planets and the neighboring stars to the sun, will enter denser regions of interstellar space. And that could affect what happens on the Earth, and it won't affect how the sun evolves probably, but it may affect the planetary system. So that is an interesting aspect of the future for the solar system, the fact that we are undulating in and out of the Milky Way in this periodic motion. Some people have even tried to they've implicated that passage through the plane of the Milky Way every 26 million years with periodic extinctions, because possibly if you go through denser environments, it could trigger an influx of comets and Earth-crossing debris, which would cause mass extinctions on the planet. And there have been claims, mostly refuted to this point, of periodic extinctions in the fossil record that match that 26 million year period. Very exciting if true, but it's not proven. Basically, the evidence is not compelling at all. But the motion is true, it's clear, and it does happen. So that's going to keep happening in the future. We're going to go in and out of the plane of the Milky Way galaxy, and the environment of the sun will change periodically because of that. Meanwhile, the other future event looming, as alluded to in the question, is the fact that the Andromeda galaxy is moving towards us at a speed of about 100 kilometers per second. Now that sounds fast, but the Andromeda galaxy is 2.25 million light years away. So if you do the math, it's going to take 2.5 to 3 billion years for these galaxies to approach each other. They're not probably going to head in a straight collision center to center. So there'll probably be some close passage, a swing by, and a sort of spiraling in of one nucleus to the other nucleus, and a series of very complex interactions between the stars in the Milky Way and the stars in Andromeda. And people have been trying to use supercomputers to simulate that. But we do think that's going to happen within about 3 billion years, which is an interesting number because, as you know, it's less than the time the sun will survive as a main sequence star. So something fairly radical is going to happen to anyone around in the solar system watching outward well before the sun dies.
All right, the next question is from Bob. Do we have a current estimate of the size of the universe? How does that size compare with the distance light would travel in 13.8 billion years? Do we have different views, different distances to the edge of the universe as we look in different directions from Earth?
So to answer the last part first, no, we have the same view in every direction. Now those super deep surveys of the sky, like the Hubble ultra deep field, that's so expensive of telescope time that we've only done super deep surveys in a handful of directions, just to make sure we didn't get unlucky and pick a weird direction. But no time these deep surveys have been checked have we ever seen any difference between the different directions we count galaxies or look at their properties. So there's no evidence at all that there's anything special about one direction versus another. And we can just sample one or two or a handful and consider them representative of what we would see across the whole sky. And when we do that, and in the size of the universe, the age of the universe is a measured number from the Hubble expansion combined with the mass and energy density of the universe and a model. The size of the universe is also a number you don't exactly measure. It's measured through a model because you need the expansion history of the universe to say what the size of the visible universe at any given time is. And the number that comes out of that model in any direction is 46 billion light years. I think I mentioned it earlier in response to another question, or a diameter, if you like, of twice that, 92 billion light years. And so immediately we see an interesting little issue. The universe is 13.8 billion years old, and that would sort of imply naively that you should not be able to see more than 13.8 billion light years in any direction, since light's the fastest thing there is. So how could the universe be 46 billion light years in any direction to the horizon, to the edge of our seeing, when the universe is only 13.8 billion years old? Remember, the calculated size comes from a model of the expansion rate. And based on our understanding of the expanding universe, that expansion rate has interesting behavior over time. We know the universe is now accelerating due to dark energy, but for most of the history of the universe, and certainly the first 2/3 of the history, the first 8 billion years, the universe was decelerating. And if you go back far enough, say to the first quarter of the history of the universe, you find that in the model, in the expanding universe, Big Bang model, any 2 points in space were moving apart faster than the speed of light. It's just straight out of the model. There's nothing weird about it. It doesn't violate relativity because general relativity imposes no speed limit on the cosmic expansion. And remember, that is the theory of gravity that we use to understand the Big Bang. So the theory, quite naturally and without any embellishment, posits a situation where for a good part of the early history of the universe was expanding superluminally, or faster than light, with any 2 points moving away from each other faster than light. And that's how, after 13.8 billion years after the Big Bang, you can end up with the furthest distance that you can see with a telescope that's roughly 3 times the age of the universe converted into light years.
Okay, the next question is from Gerald. NASA is doing some interesting work with probes, etc., but the US is not even capable of getting our own astronauts to the International Space Station. We have to rely on Russia, and relations with them are becoming more tenuous. Do you think NASA will get their act together?
Well, NASA is under a lot of pressure from different directions. They're, of course, under budgetary pressure because their budget, roughly $18.5 billion a year, has been stagnant for a decade and declines in real terms as things cost more. And it's really not enough to do all the things they want to do. Since the retiral of the space shuttle, now almost 4 years ago, we haven't been able to put Americans into orbit, indeed, without help from the Russians. And that situation will continue for the next couple of years. Now, NASA, of course, has accelerated its partnerships with the private sector. And all along, the intention was that the companies that it's partnering with at the moment for a resupply to the space station, which is just basically cargo ships, unmanned, that's Orbital Sciences and SpaceX, would eventually start carrying crews to the space station. And that's been the plan. And so the idea was that, yes, we have a hiatus in getting American astronauts into Earth orbit, but that will eventually end in a year or so. Unfortunately, the setbacks of the catastrophic loss of an orbital science spacecraft last year and the SpaceX spacecraft just a few weeks ago have put a big crimp in this plan, because neither of those accidents cost any human life. But they certainly indicate that those spacecraft are not mature enough to put people on them, put astronauts on them yet. So nobody really knows when the private sector is going to be able to launch astronauts into Earth orbit. Meanwhile, the other possibility, the Russians, of course, have their own capabilities, but their capabilities have not matured over time. They're using essentially altered proton rockets from the 1960s, and the Soyuz design is also almost 50 years old, and they don't have the money to innovate in Russia. It's a fairly poor country, despite, you know, the muscular nature of their diplomacy and their political stance. They are essentially bankrupt as far as their space program goes. So they're not going to innovate. The Chinese are going to do their own thing. They can get astronauts into orbit, but they're not going to share their capability with us because they're in a competitive stance with us. So it goes back to NASA. What is NASA going to do? And NASA does have a plan. It was originally the Constellation plan. The Constellation plan for a successor to the space shuttle, a sort of orbital capability to bring astronauts into orbit. That was canceled by President Obama in 2010. And then it was recast. It turned into the Orion concept of a manned orbital capability. And the rockets for that are being developed. So NASA has had a development program to rebuild that capacity to get people into orbit. But it's been hit by stutter steps caused by budgeting, caused by changes in political landscapes, caused by changes in NASA administrators. I mean, there's not a lot of continuity in NASA, unfortunately. And so nobody really knows when the Orion concept is actually going to be carrying astronauts into orbit, but it's at the very least 3 or 4 years away. And given the disasters with Orbital Science and SpaceX recently, they were talking about a year or two, but they are almost certainly talking about 3 or 4 years too. So now you're looking at a time that's going to head towards a decade when Americans cannot get into orbit without help from someone else. So unfortunately, the situation is not going to be rectified anytime soon.
Okay, another question about the Earth-like planet discovered, or the announcement today. NASA announced today the discovery of the most Earth-like planet yet, with only 1.5 times the mass of Earth and in the habitable zone of a sun-like star. What's the next step towards discovering life on Kepler 452b?
Well, the next step, unfortunately, is a very hard step. This unfortunate flip side of the success of Kepler is that Kepler has mostly been staring at a small patch of sky, looking quite deep, and the stars that Kepler is finding these planets around are quite faint. They're typically hundreds or thousands of times fainter than a star you could see with the naked eye, and they're typically at distances of hundreds of light years. So these are by no means, although it has got an incredible haul of Earth-like planets, none of them are nearby Earth-like planets. To do that, you would need a sort of complementary mission to Kepler, which looks at the whole sky rather than just one small patch, and looks for Earth-like planets around much brighter, much more nearby stars. Why does that matter? It matters because if you want to do this next step, this detection of life on an Earth-like planet, you have to now take the feeble reflected light of that exoplanet and disperse it into a spectrum. Also along the way, blotting out the light of the very nearby star, which is 100 million at least times brighter, depending on what wavelength you observe, and typically in optical range, more like 1 billion times brighter. So you've got an extraordinarily difficult experiment of blotting out a star by a factor of 1 billion, looking for something very, very close to that star, especially given the distance. And given the distance, the reflected light from the exoplanet is diminished by the inverse square law of light to just some incredibly feeble rate of photons, which you now have to disperse into a spectrum. That's an experiment that is essentially beyond our capability right now for Kepler exoplanets, including the one discovered today or announced today. So that's the frustration, or just the conundrum left by Kepler. Its success was in a very particular kind of experiment that netted it a haul of exoplanets that are actually quite hard to follow up, and particularly hard to do that life detection experiment. So people are now, of course, trying to do the complementary detection. They're trying very hard with different telescopes, typically quite small telescopes on the ground, not in space, to find those more nearby exoplanets. If the exoplanet, the Earth-like exoplanet, instead of the Kepler planet we're talking about, was 10 or 20 times closer, then by the inverse square law, the reflected light from it gathered by a telescope on the Earth would be 200 to 400 times brighter. The angular separation of that Earth from its star would be 10 to 20 times better. So the experiment is far, far easier if you could find a nearby Earth than a more distant Earth that Kepler's finding. And unfortunately, that's where we sit right now. Nobody can do the experiment, and it's not even on the cards in the next 5 to 10 years to find life on an exoplanet like the one Kepler just announced. But it is on the cards, and it is being planned to do that kind of an experiment for a much closer Earth-like planet, and people are looking very hard for those closer Earth-like planets. It won't be Kepler that finds it. So Kepler's contribution is essentially going to be the incredible statistics to tell us how many Earths there are in the Milky Way. And we know the number. It's about 20 billion habitable worlds in the Milky Way. Kepler isn't going to feed the big telescopes on the Earth the best candidates for looking for life, unfortunately.
All right, the next question is, if there was a star sucking gases from another star, would it look like a big point or a small line?
Typically, what happens when two stars are in orbit of each other is they will have some rotation. Stars, of course, rotate just as the sun rotates, differentially faster at the equator than the poles. And so two stars orbiting each other, if they form together in a binary system, they probably will co-orbit. So they will have rotation in the same sense as their orbit. And then what happens is the material from one star feeding onto another will sort of spread out into a disk, almost like an accretion disk. In the more general situation where the stars, say, didn't form together, where one was captured by another, they won't be spinning in the same plane. And so the material that falls from one to the other could be coming in with any orientation. It could be pouring in on the poles or on the equator or some other latitude. And then the more general way of thinking about it is in terms of what's called a Roche sphere, which is just an imaginary a potential of gravity within which material falling from one star onto another tends to fill space. And so it's called a Roche lobe, in fact. So you have a situation where the material funneling from one star into another fills a sort of three-dimensional shape that sort of looks like a sort of bowl situation, or teardrop is actually the best way to describe it. And so we could see, depending on the orbital geometry of a binary star, you can see the material coming in all sorts of ways. It could come in as a disk, just along the equator, or it could come in a more generalized shape, filling a volume in space.
All right, Bob has a follow-up question over email and about the size of the universe question. Is 46 billion light years the size of the observable universe, or some estimate of the total universe? Do we have any concept of what significance there might be to the part of the total universe that is further out than the edge of the observable universe?
It's the former, rather. It's the observable universe. So 46 billion is the distance we can see with any telescope from which light has been able to reach us in 13.8 billion years, the known age of the universe. That does not mean, of course, there's not more space beyond that. In fact, we know there has to be more space than that. Just thinking of it very simplistically, every day in an expanding universe with light traveling through it, the observable universe gets bigger every day, roughly a light day bigger in every direction. So absolutely, the region we see is growing over time as the universe gets older, and light has had time to reach us from more and more distant regions. But to answer the question of what's the limit on that, the simple answer is we don't know. There is no limit on physical space. Astronomers have found no way of determining whether there's a limit to physical space, and essentially we're bounded by space and time, and in particular we're bounded by time, and so that's what sets the observable universe.
Right. Gerald asks, initially James Webb was going to be launched in 2013, and now it's 2018. What has been the holdup?
Well, James Webb is also, you might ask alongside that, what has been the cause of the budget ballooning? James Webb was actually first budgeted at about $800 million. So you can do the math, and it's 10 times more than it was originally budgeted for. By the time it was really spec'd out as a project less than a decade ago, the estimate was about 1.5 billion. So the budget has ballooned, however you choose to look at it, and it's doubled probably in the last 4 or 5 years, even as the launch date has slipped. That's not a good situation. Why is James Webb so slow? Why is it so expensive? They're connected because James Webb is perhaps the most challenging telescope NASA has ever had to contemplate launching. We talk about Kepler, which is a 1-meter telescope, which really only does one thing. It just stared at one piece of sky, took an image every 6 minutes. Fairly simple. Well, it only cost $400 million, so it was cheap. Hubble was budgeted at $600 million when it was first conceived, now probably in the early 1970s, and it had ballooned to $1 billion or so by the time it was launched, and its total elapsed cost is also about $8 billion, but that includes all the years of operating it. James Webb is a harder mission than Hubble was. Hubble is in a low Earth orbit launched through the shuttle, serviceable by astronauts. It does have a suite of instruments that are replaced and have been upgraded 5 times. James Webb has to just work out of the box. It's a large telescope, much larger than Hubble, 6.5 meters compared to just over 2 meters, and it will deploy in orbit. So, and not in orbit, actually deploy a million miles, 1.5 million kilometers from the Earth at a Lagrange point, a gravity balance point. And so the degree of difficulty of James Webb is extraordinary because it has to be deployed remotely without astronaut assistance. It uses mechanisms that have never been used before in space to unfold mirrors, segmented mirrors, to make a 6.5 meter structure where it unfolds in space. I can't remember the number of moving parts in the James Webb overall spacecraft, its instruments and its telescope assembly structure, but it's hundreds. And moving parts in a NASA mission are always a headache, always a cost, always a risk. So it's probably the riskiest and most expensive mission NASA's ever contemplated. It's also, again, an order of magnitude more collecting area than Hubble. So it's very ambitious in almost every sense. And because it's robotic and unserviceable by astronauts, it basically has to work. And that leads you to be extremely cautious with the engineering, make your margins as big as possible on all the specs, and really not launch it until you're absolutely sure it's going to work. And so that's a lot of the time and a lot of the expense and a lot of the delays have been caused by that. It has now passed its thermal vac, what's called thermal vac testing, where the telescope assembly minus the instruments has been in a thermal vacuum chamber simulating the space environment. The instruments have independently been tested in the same space environment, which can be done at NASA centers in these deep vacuum chambers with radiation added to make it like space. And there have been some issues with detectors even on the instrument that's coming from the University of Arizona, but most of these seem to be solved. So 2018, yep, seems like they're trying to hold to it. Congress is extremely impatient, and if James Webb had more cost overruns, the NASA managers and the administrator have essentially guaranteed Congress there won't be any more overruns, or if there are, they will not come to Congress cap in hand for more money. They'll just savage the money from other budgets, which makes other astronomers in other fields very nervous. So I think it's on the home stretch, but that's in a nutshell why it's been so hard and so long.
All right, this is our final question for today. And from Lithuania, is there an alternative to chemical rockets?
Wouldn't it be nice? Yes, there are alternatives to chemical rockets. I mean, chemical rockets have been the mainstay of the space program since NASA was formed in 1959, and they're the basis of Goddard's first rockets in the 1930s. So really, we've been depending on chemical rockets for 80 years. Of course, we've been using gasoline in our cars for over 100 years, so it's not like that's moving fast either. Chemical energy, the most advanced chemical rockets, liquid oxygen-based rockets, or using sort of a very volatile kerosene-type derivatives, there's a lot of free energy in that kind of material. But of course, there's a lot of weight in it, and you have to lug all that weight just to get your small payload into orbit. And Apollo was, of course, a payload that was 5% of the mass of the Saturn V rocket that took it into orbit. So it's extremely inefficient. I mean, the fuel is cheap. That's the only good thing going for chemical fuel. These fuels are cheap. But the cost of building a huge rocket to carry mostly fuel into orbit is prohibitive. And so obviously we'd like to do better. As for the super advanced concepts, I'll try and summarize briefly because it's a big question about a big subject. The super advanced ideas of nuclear propulsion, which is natural and much more efficient than chemical energy. It's maybe 1 million or 10 million times more efficient than chemical energy. That's not on the horizon. Doing nuclear rocketry, fusion or fission rocketry is just beyond us essentially. So that's decades or maybe half a century away. So really, what's on the horizon? The thing that's on the horizon is really more simple hybrid approach. It's basically fully reusable space planes, which use air-breathing ramjet or scramjet or turbojet approaches, where they're essentially air-breathing up to an altitude of about 60 to 80,000 feet, almost beyond the atmosphere, and then they hybridize and turn into rockets to get into Earth orbit. And those prototypes of those kind of space planes, we'll call them, have been developed by NASA, have been developed by Boeing, have been developed by the Russians, are being developed by the Chinese, are being developed by the Europeans. There's probably 5 or 6 prototypes of these, and they will lower the cost to get into Earth orbit substantially. So that's the alternative. Meanwhile, in the conventional regime, Elon Musk is going back to basics with the rocket equation, and just by very, very clever and sophisticated engineering, he thinks he can reduce the cost to Earth orbit using chemical rockets, still using chemical rockets, but with reusable rockets by a factor of 8 or 10 below current levels. So those are the 2 main approaches still being followed. One's still a conventional approach, just optimizing everything with modern materials and being fully reusable. The other using a sort of hybrid technology to get into Earth orbit. So thanks for your questions. Very good. Everything from cosmology to Pluto, and I'm sure we'll be talking more about Pluto in future sessions. So meanwhile, I hope everyone enjoys the course, and we'll be back with you in a few weeks.